Okay, let's begin. So thank you everyone who's managed to stick around to the very, very end of QPL this year. This is the final talk, and it is a very special talk because Cole Comfort is talking about the ZX and calculus. And this talk is actually the winner of the Best Student Paper Award. So congratulations, Cole. You win enormous kudos, and I suppose your supervisor has to buy you as much booze as you want for the rest of the year. And let's go on to the talk. Cole Comfort.
Thanks for the introduction, Ross. And I'd like to thank the organizers for doing this conference so well online when it's the first time it's happened. So it's worked pretty well. I had lower expectations. Yeah, so I guess this year is the year of the AND gate at QPL. So this talk is kind of related to Harney's talk, and maybe I'll try to relate it a bit to that. So the title is the ZX AND calculus. So the idea is you have the ZX calculus plus the AND gate, and I give I classify, give a complete presentation of this, and also give a concrete equivalence. So it's a little motivation beforehand. So what kind of prompted me to write this paper was seeing the ZH calculus. So people have already gone over some of the axioms of the ZH calculus previously, so I won't dwell on this for too long. But essentially, the ZH calculus is like the ZX calculus, except instead of just only having Z and X spiders, you have also these H spiders. So by default, the H spiders have angle -1, and the Z spiders have angle 0. So here's the denotation of these generators. And what kind of motivated this is that in this calculus, the AND gate has a really nice presentation. So you just compose the 3-area H box with the 1-area H box, and you get the AND gate for free. So here's the axioms of the ZH calculus. So in this paper by Bakens and Kissinger. And this axiom, where is it? BA2 is the one that really I thought was cool and inspired me to write this paper, because if you look at it carefully, this is actually saying that the AND gate forms a bialgebra with the white spider. You just expand out the definition of this black spider. Yeah, so the idea of this calculus that I'm going to present is you look at the angle-free ZH calculus. So John and a co-author wrote a paper on this. But you only keep the AND gate, the phase-free spiders, and the NOT gate. So these generators. So in a way, this is like a classical kind of fragment of the ZH calculus, because you only have matrices with positive natural numbers in them. And moreover, not only do you have matrices with positive natural numbers, I actually show that these qubit matrices with natural numbers. So this is what I denote by mat sub 2 qubit matrices is actually universal and complete for this. So it's not just represented by this; it's actually universal and complete. Yeah. So here's the axioms just up front. So from 1 to 8 is just the normal axioms of the phase-free ZX calculus without the Hadamard gate. And notice I've done a bit of weird scaling so that I don't have any scalars popping up in the bialgebra and Hopf laws. So the white spider is special, but the black spider is not special. And then 9 to 14 is saying that you have an actual bialgebra with the AND gate and the white spider. And then 15 is like saying it's special, and then 17 is like this identity that Harney had, and 16 is saying that as characteristic 2. And actually, after I wrote this paper, I realized that Lafont, in his seminal paper that kind of started the whole ZX calculus thing, has a very similar calculus for Boolean functions. So here are the interpretations on the left-hand side. So on the top, you have kind of the normal ZX things without the spiders, because it's only for Boolean functions, not for like matrices or anything. And then down here, you have these identities that Harney had in his paper with Bob and Munson. So I'm not really going to give any actual proofs or like calculations or anything, but I'm going to just kind of give a broad overview. So to prove this universality and completeness, I kind of bootstrap a result that me and a co-author previously obtained. So first, you start with a prop called TOF. So this is generated by the Toffoli gate and the state preparation and measurement for 1. So this is like classical reversible circuits. And then I change the presentation of this category. So actually, I add 2 generators corresponding to the unnormalized plus state and effect. And then I change the presentation of this category to be given in terms of monoids and comonoids interacting via distributive laws. And then finally, the third bit, which is probably the most interesting part, involving the least amount of calculation, which is what I'll talk about today, is I'll use the completeness and universality of TOF for that I proved in the previous paper to show that this extension ZX and is complete and universal with respect to this interpretation into qubit natural number matrices. So most of the talk will be devoted to reviewing and developing the theory of restriction categories. So I'm sorry I have to do this, especially if you've heard my previous talks at QPL. So yeah, a restriction category is a category with a restriction operator satisfying some algebraic identities. And the idea of this restriction operator is like it's a generalization of taking the restriction of a partial function. So the restriction of a partial function is you just take a partial function and restrict it to the identity on its domain of definition. So this allows you to generalize isomorphisms to so-called partial isomorphisms. So a map F has a partial inverse G when F composed with G. So I'm using diagrammatic notation. F composed with G is equal to F bar, and G composed with F is equal to G bar. So it's like their inverses, except only up to partiality, right? So it's not the identity; it's like a partial identity. And what's really nice is these restriction categories are partial order enriched. So you can say that like one map is less defined than the other when you have this this equation that holds, right? Because you're precomposing G with the like domain of definition of F. So the obvious example is sets and partial maps. I think previously this was called P-fun, but I'll call it PAR in this talk. So if you consider a restriction category in which every map is a partial isomorphism, then we call it Calkin and Lack called this an inverse category. And there's a really nice presentation of inverse categories in terms of having a Dagger functor satisfying these extra 2 equations. So I mean, if you look at the third equation, this is actually just R2 here, saying that the restriction idempotents commute with each other. So yeah, in this setting, this Dagger functor takes a map to its partial inverse. And called the subcategory of partial isomorphisms of par pinch. So sets and partial injections. That's where the name comes from. Yeah, so a lot of restriction categories arise in a particular way. Namely, if you have a category with pullbacks and a class of monics M close to pullbacks, then you can form the partial map category with respect to this class of monics. So the idea is the maps are spans, and the left leg of the map is a monic. So it's like, you can think of it as like an inclusion. So I've suggestively drawn it in this way. And then the apex of the span is the actual honest domain of definition. And then the right leg is like the total function on this domain of definition. So you can compose these maps with pullback, and because you have this inclusion on the left-hand side, then you don't get actual functions, you get partial functions. And the restriction operator is given by just copying the inclusion, the monic, to both sides of the span. Yeah, and of course, partial map categories are restriction categories. I mean, I think restriction categories kind of developed from this idea. And yeah, and the partial map category given by sets and all the monics in sets and functions is just par again. So this is just an alternative presentation of par. Yeah, also sets and partial injections can be represented as spans where both of legs are monic. So both par and pinch are partial map categories in the sense, except pinch is also an inverse category. And what's kind of interesting is they have a tensor product given induced by the underlying tensor product of sets, or Cartesian product of sets. So it's the pointwise Cartesian product. And actually, if you think for a bit, this tensor product isn't actually a categorical product because there's no projection maps. So one has to ask, what's the appropriate weakening of the Cartesian product for restriction categories and for inverse categories? So the first one for restriction categories, so Cartesian restriction category is a category where you have this pullback diagram, but it only commutes up to the two cells. So where these two cells you recall come from the partial order enrichment of restriction categories, saying that the one side is less defined than the other side, because you can't ask for there to be projections which are actually honest to God projections. And a discrete Cartesian restriction category is a Cartesian restriction category where the diagonal map given by copying the identity is always a partial isomorphism. And again, par is a discrete Cartesian restriction category where this diagonal map is given by the span, where on the left it's equals, and on the right you have just the diagonal map in sets. And the proper notion of like a Cartesian inverse category is slightly different than for restriction categories, because you have to also consider the partial inverse of the diagonal map. So I'm kind of sweeping a few technical details under the rug here, just so I can give some nice diagrams. But if you have a symmetrical modal inverse category, it's called a discrete inverse category if you have this semigroup and co-semigroup that interact together to form a non-unital Frobenius algebra that's special. So semigroup, co-semigroup, special, Frobenius. That's also natural, so it copies all maps, and compatible with the monoidal structure in an obvious way. And of course, pinch is a discrete inverse category. Yeah, so these are both the right notions of generalizations for products of these two things, because the total map category of a discrete Cartesian restriction category is a Cartesian category. And there's an equivalence of categories between discrete Cartesian restriction categories and discrete inverse categories. So this theorem was in Brett Giles' thesis. So to get from discrete Cartesian restriction categories to discrete inverse categories, you take the subcategory of all the partial isomorphisms. But for the other direction, it's actually kind of interesting construction which you came up with. So this construction called the Cartesian completion has the same objects as the underlying discrete inverse category, except the maps are now like kind of slices. You add an extra object in the codomain, and then you quotient out by this relation here. And the composition and tensor are given in obvious ways, but the way that I like to think about this is it's kind of like Krauss maps in the CPM construction. And I'll elaborate a bit on that further. And so you're kind of like you're copying the codomain on the top, and then on the bottom you have this kind of ancillary space, and you're undoing it and then applying G to it, so you're transforming the ancillary space of F and G between each other. So the Cartesian completion of sets and partial injections is actually par, which is pretty important for this talk. So when I initially saw this construction, when I was reading Brett's thesis, I immediately thought, oh, this looks a lot like Krauss maps. What's the relation? And actually, there is a relation. So if you have a discrete inverse category X, and as a technical requirement, I have to ask that it embeds in a compact closed category, which I'm not sure if it holds in general. But you can construct a category of quantum channels of X. So this is kind of like copying the work of like Selinger and Kuka and everyone. So this is kind of like Kuka's CP infinity construction, where it's like the CPM construction, except you flatten out the maps. And you said the two maps are equal if and only if these Krauss maps are equal. Well, I prove in the paper that the equivalence relation here for the Cartesian completion is the same as, it can be restated in this way. And actually, if you look at this a bit carefully, this is precisely the full subcategory of the Karoubi envelope of the CP star or CP infinity construction, where the objects are given by the decoherence maps. So actually, this is like the appropriate notion of the category of classical channels of X, whereas on top this is the quantum channels. So that's pretty cool, and I use this to prove another result, namely that the Cartesian completion of X can be presented in terms of generators and relations instead of having this nasty equivalence relation hanging around. Because if you think of the CP star construction as like decohering and then having a discarding map, the discarding map is actually like the co-unit for the Frobenius algebra, because recall the Frobenius algebra originally neither had co-units nor units in a discrete inverse category. So if you add a co-unit to the inverse products of sets and partial injections, then you get sets and partial maps. So I think that's pretty cool. Adding discarding to sets and partial injections gives you partial maps. So now I'll get to the actual like thing that people might be interested in. So I talked about this prop TOF. So these are the generators up top here, and I've just annotated the Toffoli gate by its action. So it acts on the first two qubits as the identity, and on the third it multiplies the first two and then adds the third. So this, then you have the one preparation and measurement. You can define the controlled NOT gate, the NOT gate, 0, and then from this you can get the inverse products by applying the controlled NOT gate to the 0 state and the 0 effect. And the partial inverse is just giving by flipping the diagrams around horizontally. So here's a bunch of ugly axioms that I came up with, but the idea is to simplify this. So I won't like review any of them. And yeah, in this paper, I showed that this is universal and complete. I should add, I missed this out here, for partial isomorphisms between ordinals of cardinality 2 to the n for some n. So in other words, this is monic spans of this form. And of course, the tensor product is the same as impinge. It's pointwise Cartesian product. So yeah, the idea is you add a unit and co-unit instead of just adding a co-unit. So of course, if you add a co-unit, then you get like, some subcategory sets and partial maps where the objects have the right cardinality. But how do you also add a unit? So the way that I do this is by this distributive law. So this is like the method used by Lack in his paper of composing props. So I compose maps with TOF plus a counit and maps with TOF plus a unit on the right over TOF. So you can think of this as formally having maps in TOF plus a unit and having composed with formal maps in TOF plus a counit, where you can kind of slide the components of TOF in between like both tiles. So this distributive law just says that you can take the unit and counit and cross them over. So in spans, what you get is, this is like saying you have a span with a monic on the left-hand side composed with a span with a monic on the right-hand side. So like on the left you have a partial function, on the right you have a copartial function, and then this gives you a partial function composed with a copartial function, so that you can use the TOF to like kind of push it all together and then actually compute a normal form to get completeness and universality for this category of spans. So here's this lemma: TOF plus units and counits gives you a presentation for spans. So spans up to isomorphism between finite ordinals with cardinality 2 to the n for some n, with the pointwise Cartesian product as a tensor product. So initially when I saw this, I was like, this is a weird category. Just spans, like why is this equivalent to spans? Doesn't make sense. But then I read this paper by I think Bruni and Guiducci, where they said that the category of spans and finite ordinals is equivalent to matrices over the natural numbers. So the idea is the elements in the feet of the span are like the basis elements, and if you look at the preimage of the span, the number of shared elements in the preimage correspond to the entry of the matrix. And if you do some work, then you can see that the monoidal product actually becomes like the Kronecker product, because it acts like the product on the basis elements. So because full subcategories reflect like limits and co-limits or whatever, then you get immediately that adding units and co-units to TOF gives a presentation for qubit matrices over n. And you can think of this as like qubit multi-relations as well. So like relations are like matrices over the Boolean semi-ring. This is just matrices over the natural numbers. So this is my final slide, or second final slide. Yeah, so if you look at the counit in this category, this corresponds to having span on the left-hand side where it's equality. On the right-hand side, you have this discarding map in sets, right? So the map just taking you to the terminal object. And as a matrix, this is this vector plus. So you can construct the AND gate from the Toffoli gate and these generators in this way by like discarding with the plus. And you can go the other direction to get the Toffoli gate. So I mean, this is well known, but so by translating between TOF plus the counit and unit and ZX, then you actually, after like tons of calculations, you get this theorem that they're actually isomorphic as like dagger monoidal categories. So that's pretty cool. So yeah, to conclude, there's a lot of things that could be done here. So like, first is relating this to what other people have done. So Harney has a paper. I don't know if it's published yet on presenting semi-ring models of the ZX calculus. So this would be like the natural. This would be subsumed in as the natural number case of his calculus. Except I think the identities here are pretty nice and canonical. So you can get the triangle generator And then you can also get the Hadamard boxes from the triangle. So there's obviously some relation to the phase-free ZH calculus, but I should note you get the natural number Hadamard boxes, right? Because you only have positive natural numbers. And it also would be interesting to see if you can get nicer axioms for the phase-free ZH calculus. And if you could generalize this to qubits, also it'd be nice to find a normal form using the fact that I've presented this category in terms of distributive laws between monoids. There's this correspondence between distributive laws and normal forms. So I have a bunch of references, probably way too many to read. And I have a nice proof to show how nicely proofs work in the setting. And that's all.
Great, thank you very much, Cole, for the talk. I have done my clapping, so everyone else can join in. Right, so we have already a question from John van der Wetering, who says, do you have examples of discrete inverse categories that aren't PINV? And I assume he means pinge? I'm not sure.
Yeah, so I'm trying to remember exactly the example, but in Brett Giles' thesis, he gives one example where it's like some type of some category of semi-lattices, which apparently is really canonical. I'll respond in the chat when I look it up. But yeah, I'm just normally used to working with subcategories of pinch because it's so nice.
Okay, so a question from me then, because it was a little bit lost in the presentation. You said that the this model, this ZX and calculus, is a model of natural number matrices. So can you just briefly show us how you get the bigger numbers than 1 and 0 in this this formalism?
Bigger numbers than.
So I want the matrix that's like 1, 2, 1, and 0.
Well, like I didn't do it constructively, but or I didn't do it explicitly rather, but so like you can construct the triangle gate, right? So I mean, you could use whatever method like Harney has in his papers for like normal forms of things explicitly. Yeah, using the triangle gate, because this is like, then you have this H box, right, which is like matrix of all ones except the bottom right is like n.
Okay, I think I see how to do it. Let's go to Stefano Gagosio, who'd like to know about the generalization from Z2, i.e. XOR and AND, to arbitrary finite rings or fields.
I haven't done anything. I think I talked to Stefano about this, but I haven't actually done anything. So this is like future work is like a slide for things that I haven't done or may never do.
Okay, and I think that seems to be all the questions that we have from Slack for just now. And since we are at 2 minutes to 5, I think this is a good time to call a halt to the proceedings. So first of all, I would like to offer thanks to Cole for the talk, and also congratulations on winning the Best Student Paper Award. And since I am the final chair of QPL this year, I guess that means that it's up to me to say a big thank you to all of the organizers and the local, the PC, etc., for everything they did here. It's the first time we had to do a virtual QPL. Everything is new, and despite the fact we had a couple of hitches, I think that this went about as well as it could have possibly gone. So I want to say a big thank you to the organizers of putting this event together. Oh, God damn it. Right, and with that, I'm going to stop broadcasting and invite everyone to join us in the Pub Social channel for further discussions and also lessons on how to keep our laptops charged up. Louis. All right. Have a good time, everyone. Goodbye.